¿Yo qué? ¿Yo qué?
Que si ya cambiamos de speaker.
Sí.
Sí.
Buenas tardes, vamos a comenzar nuestro coloquio del día de hoy. Tenemos el gusto de tener como ponente al doctor Alberto Carramiñana Alonso. El doctor Carramiñana es egresado de la Facultad de Ciencias de la UNAM, donde cursó la licenciatura, y fuimos compañeros de generación, por cierto, y la maestría, habiendo sido estudiante posteriormente en el Instituto de Astronomía. Obtuvo el doctorado en Astronomía de rayos gamma por la Universidad de Durham, en Inglaterra. Después un postdoc en la Agencia Espacial Europea. Regresó a México para integrarse al Instituto Nacional de Astrofísica, Óptica y Electrónica en Tonantzintla, Puebla, donde fungió como coordinador de astrofísica y director general. Es coautor de numerosos artículos de investigación científica y trabajos en congresos nacionales e internacionales. Es miembro de la Academia Mexicana de Ciencias, de la Unión Astronómica Internacional y del Sistema Nacional de Investigadores. Formó parte del Consejo de Colaboración del Gran Telescopio Milimétrico Alfonso Serrano y del Comité de Seguimiento del Gran Telescopio Canarias. Es miembro fundador de la colaboración HAWC, dedicada a la operación y explotación científica del Observatorio de Rayos Cósmicos y Rayos Gamma, situado a 4.100 metros de altura en el volcán Sierra Negra. El día de hoy, el doctor Carramiñana nos va a platicar sobre el cielo visto en rayos gamma de muy alta energía, 10 años de operación del observatorio HAWC. Le hemos solicitado nos imparta su charla en inglés, debido a que hay personas que no son hablantes de nuestro castellano. Adelante. Bienvenido y muchas gracias.
Sale. Muchas gracias. Nada más antes de switcharme al inglés, pues me da mucho gusto de estar aquí con colegas que conozco desde hace décadas, ¿no? Y pues bajita la mano, puse esa nota de que yo fui estudiante aquí porque pues esto es un poquito como mi casa. Now let me switch to English, hoping that the students will understand what I'm saying. Slides are, I believe, in Spanish, so everybody should be able to understand. So I'm going to talk about the sky as seen in gamma rays and also a little bit of cosmic rays by the HAWC Observatory, now that we are really very close to the 10 years of its formal inauguration. So before I start, let me say that I'm very glad that this colloquium has the name of Arcadio Poveda, who was I believe he was the coordinador de la investigación científica when I was a student here. And then later he was a very good advisor of Alfonso Serrano while in INAOE. Here you have a photograph of a very long time ago. And he advised very much Alfonso, not just on the institute, INAOE itself, but also on the LMT. So you can have here having a drink, high altitude drink, and discussing things on the LMT. And that also brings me to one of the first steps that colleagues of UNAM, INAOE, and other places did to have HAWC in Mexico, which was in the Cosmic Ray Conference, 2007. That was held in Mérida, and of course, Arcadio was there in Mérida. And in fact, he grabbed me at the dinner of the conference because he was very worried about the LMT. You know, 2007 was some months after the inauguration. The telescope was not operating. What's going on? And you know, he dragged me, and I was with the pressure of having organized a meeting, a few drinks, and I think we talked for like 5 hours. I don't know, very long time. So anyway, so let me tell you about HAWC now. Again, with the pleasure of being in the Arcadio Poveda seminar. So I'll try to put this into a more general perspective, on historical perspective even, on the first arrays, surface arrays made to study cosmic rays, how they started in the some time ago. A little bit, not too long, on the HAWC project that led to the HAWC Observatory, inaugurated in March 2015. So we're really there. And then I'll try to go more on HAWC papers. So I did a little bibliography study, a little bit what I would like to show to people on the SNI when they say that I'm inflating my numbers. Well, you know, that's the way they are, the numbers. And a little bit on the future, which is like getting there. So, you know, cosmic rays, they were discovered in over 100 years ago. They're the cause of ionization in the air. But what we see, this is the ionization versus altitude as taken in balloon flights in 1913, 14. By Hess and Kolhoster up to 9 kilometers. And basically what ionized air are particles, high energy particles in the atmosphere. Now these high energy particles are not directly the cosmic rays that are in interstellar or interplanetary space. They are secondary particles that are produced in the atmosphere by those particles with extremely high energies. That was deduced a long time ago. Should I? Okay. And don't show this again. Never, ever. No. Okay. So that was shown by Pierre Auger, who the people used to start with 1 or 2 detectors of particles, and they saw that they could put the detectors away and they would have coincident recordings. Of course, that was not with computers or anything like that. That was very artisanal. So Auger saw that there were the number of coincident matches between 2 parallel counters, horizontal, and you could take them as far away as 10 meters, even 100 meters, even 300 meters, and still have coincident particles. And he deduced that there were particles all over the place covering up to those distances. And then he deduced that there were 10 to the 6 particles within that sort of space, and in each one had around 10 to the 8 electron volts. You had a primary particle leading to 1 million particles, and the primary had to be of around up to 10 to the 15 electron volts. Let me see. Sorry. I need to press to do click on my. No, yeah. We have a little problem here. I see the next slide on the screen, but not in here, but not in there. Aquí cambia, pero allá no. Aquí ya es la siguiente. O yo estoy desconectado de internet. Sorry about this. Keynote. Es Keynote. Ay, dale. Bueno, aquí. Okay. All right. Okay, that was 1939, and so that's that's a little bit the image that we can get into our heads when they talk about particle cascades given by cosmic rays. But actually, they're not quite like that. After the war, in fact, Bruno Rossi was, he did great contributions to the study of cosmic rays. He had to leave Italy during the war because of Mussolini. He arrived to the US, and then he set the group to study cosmic rays in the US. So they started putting 3 detectors on the ground on different arrays. So his group demonstrated in 1953 that in fact, there is all these particles, all the particles in a cascade arrive very close together to the floor, in fact, making a front of just 2 meters, 2 meters, and traveling basically at the speed of light. So you could get the direction of those, of the axis of this shower on the floor. So just using 3 detectors, they managed to measure the position on the sky. So here the circles represent the zenithal distance, just with 3 detectors. That was 1953, and basically they planned to do something better, so they created a larger array of about 15 detectors, separated by something like 300 meters, and these detectors were scintillators. First, liquid scintillators, and that was installed in close to a forest in Harvard, Massachusetts. And it happened that during a storm, the liquid scintillators got fire and almost made a fire there. So they developed within a year plastic scintillators that don't get fire. So this array worked for a few years there, and basically it demonstrated the power, the spectrum, and the isotropy of cosmic rays. Eventually, it went to La Paz to study cosmic rays at high altitude, and it was a precursor of the big particle detector. So this is from the paper Clark et al., the same group of Bruno Rossi. They extended the energy spectrum from the measurements of HAWC up to 10 to the 18 electron volts. So the mystery was, how do you get objects that can create particles of that energy? And you couldn't see them on the sky. So this is a distribution of their events on the sky. And there is no accumulation along the galactic plane. And basically the answer is that cosmic rays are charged particles that don't travel in straight line. They diffuse all across the galaxy, and they lose any positional information. I'll skip this one. So that was like the first ray detector. Some time later, instead of scintillators in Harvard Park in England, when I was a student at England, in fact, it was still running, they made the first detector with water, basically taken advantage of the Cherenkov light produced by high energy particles when they enter water. And that was very successful. It ran for like 20 years. And as some of you know, the Pierre-Auger Observatory uses particle Cherenkov detectors. I'll put these in fact, some of these are made in Mexico, and they're up there in Argentina with water and just a phototube to detect the secondary particles. And around the 1980s, it started to have the inquietude to make an array that was able to detect photons that travel in straight light. And basically what you had to do is a method where you could discriminate gamma rays from cosmic rays one way or another. And one advantage that was clear is the altitude. So they started, the first array was the Cygnus array in New Mexico. It didn't manage really to detect gamma ray sources, but then came the next 2 detectors. And there was already a competition between the groups in the US, in Los Alamos in particular, and the groups in China who benefited from higher sites. All right, so this is a letter by Hans Bethe to the director of Los Alamos in 1984, just proposing the first detector, water detector of this kind at high altitude. That led to the Cygnus array, which then led to the next array, which was Milagro. This is a very basic artist conception in the 80s. So Milagro was developed. It started working in the late 90s. And it was basically a large water detector around 50, 80 meters, surrounded by small water tanks, a little bit like those you saw in OJ. They were not red, but you had to tag them in red because otherwise you wouldn't be able to see them, right? And Milagro was kind of successful. It managed for the first time from a ground array to separate successfully gamma rays from cosmic rays and detect sources. It detected sources in the Cygnus region, in the galactic plane on the direction towards the center, which is like here, the Crab Nebula, Geminga, Markarian 421, and its competitor, the Chinese group of Tibeter Shower Array 1, also reported the detection of the Crab and Markarian 421. Basically, the one difference is the Earth Shower Array in China was made with plastic scintillators, not with water technology, which was in fact a disadvantage. And so, because you couldn't find a place at 4,000 meters in the US where you could put water and it would remain liquid, the groups of Milagro looked south and they found us. Here at UNAM, INAOE, they went also several places, and they proposed in 2006 a larger experiment, better design, and at higher altitude than Milagro, and that's the proposal for HAWC. Here you see, basically this is how many, when you start with a gamma ray, very high energy gamma ray photon of say around 1 TeV, this is how it develops, it reaches a maximum, this is how many electrons are in this shower until it reaches a maximum at something like 6,000 meters and then it starts fading down. And you can see the difference between B at 4,100 meters, being at 2,300 meters, this is log scale, so it's a factor almost of 3, or around here, 27 corresponds to sea level where you get very little. So we got on this in 2007. We formed the US-Mexico collaboration in Mérida. I think probably not the same the next day where I had my drinks and chat with Arcadio, hopefully before that. And we have kept working here. So not sure if I say, well, Andres is certainly in that picture. Arturo is probably on the same picture. Abel might be there. Ernesto, so Analia, a few of you are here in the picture. That's one of our last meetings in Puerto Vallarta. You know, after so many Zoom meetings, we really needed something like this to talk. Yeah. So the HAWC collaboration is a large collaboration. I believe is one of the largest collaborations, scientific collaborations where Mexico is involved. Mexico is with a dozen institutions, 4 institutes of UNAM, INAOE, and some other universities, around the same number of institutions in the US. Maryland has the funding of the National Science Foundation. Los Alamos had a founding from Department of Energy, and those are the pioneer groups in the US. And then some of the students from US and even from Mexico have gone to places in Europe, Asia, and also even in Costa Rica, where we have right now also a student from INAOE up there. So basic advantage of Mexico, in fact, we competed against Bolivia and China to make the experiment here in Mexico, was to have a site with some basic infrastructure. And this is close to the Pico de Orizaba in the Tliltepetl, the Black Mountain, next to the Mountain of the Stars. And somewhere here in the valley is the HAWC Gamma Ray Observatory. This is taken from a flight getting to the Puebla airport time ago. So it's one of those cases where you make something, and then that helps you to bring something new. So around 2000, INAOE started building the Gran Telescopio Milimétrico. Alfonso Serrano was in charge of that. And basically that led to having a road, electricity, internet that reaches up here to 4,600 meters. So around 2009, once we had some little money, not yet the full funding, we could extend here the electricity and the road and the power, some 700 meters to reach HAWC, 500 meters below 1 kilometer further north than the GTM LMT. So I'm not going to describe HAWC in detail, but basically these are our 300 detectors, 4 phototubes on each one, so we have 1,200 channels, and we cover an area of 22,000 meters. So if you remember the experiment made in the 50s by the group of MIT, it's actually smaller, but it has almost 100 times more channels in an area that is like 5 times smaller than the array. So the dense sampling is very good for trying to distinguish gamma rays from cosmic rays at our energies. So we completed in 2014, actually on time, on budget, and on the specs. And then we could have basically our big inauguration party in March 2015, on the 20th of March 2015, which also happened to be Equinox Day. So we were kind of lucky with that. Franz Cordova came. Actually, she had 2 interests, not only the science, but also she wanted to go to the top of Citlaltépetl, which was kind of an issue. It wasn't that easy. So at the end, we went the following day to Cacaxtla. No, not to Cacaxtla, to Cantona. And of course, there was Saturday, 21st of March. So there were so many people trying to grab the cosmic energy on Equinox Day. It was wonderful. They really loved our guests from the NSF. That was so much fun. So if you see that, take us to a week tomorrow. It will be the 10 years of the HAWC Observatory inauguration. Of course, it had been running a little bit for a while, no? And basically the database, which is kind of the legacy that will persist after HAWC is done. We really don't want it to be done, you know, we want to keep going for much longer, but the database is here at the UNAM, Instituto de Ciencias Nucleares. It has already like 10 petabytes, and we want to keep building more data on it. Okay, and 2018, you know, we knew that the Chinese were plotting something. So we made an expansion that was already in the original plan to that we could make an expansion of the observatory, putting some of these rotoplast tanks, 2,500 cubic meters each, and 300 of them, 345 or 250 of them around here. The slope is such that this is the lower place, the lower part of HAWC, this is higher. And I'm very sorry to tell you that a couple of these have disappeared, and there is a road here, and you know the sort of things that we have to deal in here in Mexico. The good thing is that they didn't steal, I think, the photo tubes. All right, so we had kind of fun, but we were not productive from the point of view of papers and all that. For a few years, 2016, when the proposal came to Mexico, to say 2011, 12, when we started getting the first data. So this is the papers that we have produced. So this is the inauguration, and since the inauguration, when the array was completed, this led to a boom in the year 2017. So now we're at a rate of about 10 papers a year. We produce 88 papers. I think there are also like 3 or 4. These papers I take from my authorship, and I think I have missed like 3 or 4 that I have not signed. And here last year was very productive with 14 papers. So here is a plot. is log scale. So this is how many authors we have in those 88 papers against how many citations. And of course, if I were to put, in my semblanza, I'm the author of so many papers with so many citations, I have to say that these two dominate my citations, and I wouldn't feel that comfortable, really. Because if you see in log scale, these two are like half of those citations on just two papers that have over 1,000 authors. So I cannot say that I made all those, that production. But still, they're part of the work of the collaboration and how we are contributing. So I can distinguish, and I'll tell you a little bit about these categories of papers, more or less quickly, about these two papers. As you can see, 3,000 authors. And I wouldn't be surprised if about half of the people here are co-authors with me in this paper, and you also have all those citations. And then this one with 1,000, pretty much 1,000 and 1,000. And then we have these papers, as you can see, not so many citations, that are papers between inter-collaboration papers. And then these are the ones we can identify as HAWC-only papers. I'm not going to tell you about all these papers, just give a few examples. So these papers are famous now. This is the detection of gravitational waves from this event on 17 August 2017, which was followed by a gamma ray burst. And this one is a neutrino detected by ice cube, which is consistent with the flaring of a BLAC object. So very quickly, this is not the author list. This is the group of collaborations, each of how many authors that make this paper, 3,677 authors. In fact, how many of you are authors here? No, they don't want to check that. Okay, many of you. So here is a HAWC collaboration as part of this paper. And basically our contribution, I cannot say that we made as much of a contribution as LIGO or some of the follow-up observers. Basically, this event was a gravitational wave, a slow one. In fact, Alejandro might tell you more on this one. And then 2 seconds after, there was a faint gamma ray burst that was followed error boxes by Fermi, GBM, then detection of NGC 4993, until then obscure galaxy, now a very famous one. And then there was this transient. And basically, this was, HAWC almost didn't make it to the author list, because that was just at the south of our field of view. Our field of view moves on the sky like this every sidereal day, and then a few hours after the gravitational wave, we pass through the field of view, and we set an upper limit. It was a non-detection of TV gamma rays from this event. We did a bit better in this one. 1,000 authors, 1,000 citations, and of course this list is smaller. Still, you wouldn't put the author listing here. And basically that was a neutrino, 290 TeV, detected by IceCube, going more or less horizontal, so that means near to the equator. And it matched a flaring BLAC object, Texas 056. Here, this is the image by Fermi Gamma Ray Space Telescope, which quoted in a high state. It had not been, I'm not so sure if it had been cataloged until then, but it was faint, and it was here in these days, it was bright, and then it led to the detection by magic at hundreds of GeV. And HAWC works like 10 times higher energies. So we had a detection, we had a chance to detect it. It was, again, we were not lucky, not in our field of view. We basically had to wait a few hours, and then we didn't detect, but we set an upper limit. So this is the multi-wavelength spectrum from the radio, optical, X-rays, and then these are the Fermi points, lat Fermi points. This is at the moment of the outburst, and the neutrino. This is the archival data from Fermi, so it was definitely flaring by a factor almost 10. This is magic, and this is the upper limit that HAWC set at the time of the flaring, and this is the archival upper limit. We have not detected that AGN, and it's not surprising because some of you may know, I could answer that in the questions, that we cannot really go beyond redshift, say 0.3 because the universe happens to be opaque to TeV gamma rays. Okay, let me tell you about a couple of these papers. We have now 8. There is a new one. This is kind of new paper, 0 citations so far, but it's new. A few papers with collaborations. Basically here, we work a lot with the IceCube collaboration. That's University of Wisconsin. It's a leader in IceCube and is also a numerous group in the co-collaboration. And here with some other gamma ray groups like HES, Veritas, LAT, and MAGIC, right? So I'll just give 2 examples. And this one I like very much. This is the result of the PhD thesis of a Mexican student that he graduated from the University of Guadalajara, Juan Carlos Díaz Vélez. He is at Wisconsin with IceCube. And basically, this is, you saw that map of the cosmic rays detected by the MIT experiment. This is the same at lower energies done with HAWC and with IceCube. So this is the coverage of the sky. This is the cosine of the declination. This is the South Pole. This is the North Pole. And blue is the HAWC data. And this kind of color is the IceCube data. And we only miss 5% of the celestial sphere. So it's like if you want to see the dipole and multiple moments of the distribution with CMB, well, we're missing 5%, and we're doing the same thing with cosmic rays. And we have also here an interval. Basically, we measure at similar energies, and we can cross-calibrate our joint data here. This is then the work. So this is the multiple moments. So the distribution is not completely isotropic. It has a nice anisotropy, and not too dissimilar to the one in the CMB. And part is due to the motion of the Earth. So these are with the principal moments, so let's say dipole, quadrupole, octupole. When you remove from the data, you get here an enhancement in some particular direction. This is like 1 part in 10,000. And this more or less matches the direction of the shock, the Helios shock, where we believe particles are accelerated. In fact, the duration radius of these particles at 10 TeV more or less matches the size of the solar system. All right, let me go to another one. So this is also a nice paper, Abdallah et al. Just one slide on this one. Is a joint paper of the galactic plane by HAWC and the HES collaboration. So the HES collaboration has some Cherenkov telescopes operating in the southern hemisphere, in Namibia. And basically for years they have been scanning the galactic plane. And again, there is a zone that matches the galactic plane survey of HES and of HAWC. So this is the interval, basically is from galactic longitude 10 to galactic longitude 60. So this is the HAWC map. And this is the map seen by HES, which has those Cherenkov telescopes, atmospheric Cherenkov telescopes have better resolutions. So basically they degrade, they're better for point sources, but not as good for extended sources. So they degraded their signals to match our resolution and our integration, and more or less try to mimic our map from their data, right? So there's some difference, as you can see, and we had a few comparisons, and so we could more or less compare the ups and downs of each technique. And one of the conclusions is that having a water Cherenkov surface array is good. You don't only need a CTA array of Cherenkov telescopes, but to have a Earth surface experiment is also good. So I won't go in all this, but this is more or less now the distributions of HAWC-only papers. Basically, we're about 100 co-authors in each paper. And as you can see, we have, I put this line is about 10 citations per year. So these are our highest impact papers, more or less listed here. And you can see more or less what we do just by checking on the list. So we have the Geminga paper, I'll show you this. We have a couple of catalogs, in fact, 3 catalog papers. These are the second and third HAWC catalog. This is the third one is our catalog of high energy, more than 56 TeV photons. And these are very few sources. We have some crab papers. I'll show you the last one, which the crab is a very good source because it's almost a calibrator on the sky. So we have not just to study the crab, but it helps for us to study our own instrument and its performance. Cygnus cocoon is a star-forming region. Normally, most of the sources that we study, like Geminga, are associated to neutron stars, but not Cygnus, which is associated to star formation, or SS433, which has a black hole there, so that made it to nature. I won't show it here, just if anyone asks, we search for dark matter. We have lots of papers on dark matter searches, and we have some limits. This is our most cited one. We have this source, which is southern source, I'll talk, and one of our latest sources is the sun. So we have the highest energy detection of the sun, and I'll show that one quickly. Okay, so this is the crab. We have, I'll tell you 3 papers on the crab. The first one is the validation, just checking that HAWC was performing well and what we could see. So here you have the spectra. This is 10 tera electron volts, 100 tera electron volts, and this is the first feed we did to the crab spectrum, a log parabola feed with systematic uncertainty. So the gray darker band is the statistical, the other is the systematic uncertainty, and more or less in agreement with other experiments there. The second paper, we developed 2 techniques to better estimate the energy of our events. So one is more or less copied from the PROG experiment, where you map the distribution of events of your shower, and you see what happens at 40 meters from the core. And this axis basically maps the energy of the event. And then, of course, now, artificial intelligence, neural networks, all that is very fashionable. So some students develop this neural network, basically counts how many particles you have in each of a 10-meter bin. And the neural networks sort of, it has trained with simulations, all that, and it tells you the energy is such. And it has a pretty good match. So one is a map of the crab generated by the ground parameter, and the other with the neural network. And with these 2 techniques, basically, we got the same spectrum, and we got now beyond 100 tera electron volts, extending much more from what we had before. So, it's more you work with your experiment, better you know how it works, and we're in there. And basically, the last paper from last year is, a better response. This is what we call the PAS4 technique. This is PAS5, which is an improvement, and basically we've gone through this dotted line to here in terms of the effective area of our instrument, and also our point spread function also got much better. All right, so this is what we see. You may remember the map that Milagro got. This is the 3rd catalog. We're working on the 4th. It probably goes out this year, we hope. We're really trying to get that. So you can see a much sharper galactic plane. Cygnus region is here. We have a source further here. And now in fact, with PAS5, the new technique, we are starting to see the galactic center, which I won't show show it there. Right, this is now, that map has a median energy of 7 tera-electron volts. If you go to over 50 tera-electron volts, now you get these few sources. So these are from the region of Cygnus, and this is from the first quadrant of the galactic plane. Basically, this is Cygnus that we see at higher energies, and then this part of the galactic plane are in those. And very few sources at 100 tera-electron volts, one here, and these couple of sources. Actually, with the past 5 now, we're seeing more sources beyond 100 tera-electron volts, which is interesting regime because electrons have trouble producing gamma rays when they have energies much beyond 100, more like 200, 300. Once you get those energies, your sources are more likely to be proton accelerators, not lepton accelerators, right? So that is one thing that we're trying to get there. And this is our most cited paper, the discovery of these very large halos around the Geminga and the monogem pulsars. So the story goes that you have something like the crab pulsar that is very young, 1,000 years, and is, has a very strong wind that is pushing the galactic medium. And then electrons slowly start diffusing. And when your object is like 20,000 years, they have diffused here, but in fact, they have diffused slower than what you expect just by the properties of interstellar medium. And at around 1 tera-electron volt, so this is more or less how much they diffuse. These two sources are very near from us. So this is the Earth, a bit bigger than it really is. And these are 250 parsecs distance. That's the distance to these two objects. And these halos extend to tens of parsecs. And basically is the diffusion of 1 TeV electrons that gets further. And these electrons, by inverse Compton scattering, produce these gamma rays. Electrons that have a smaller energy, they diffuse very slower, so they don't get that far. So it's hard for Fermi to see those halos. And electrons that have larger energy, they lose it very quickly. So 1 TeV is like the bench, the spot, the hot spot to see these things. So basically, this is just the extension of those couple of halos that we detect up to like 20, 30 parsecs from the center, the central object. And this is kind of a new sort of object, these TeV halos. And this is a paper where we are not in this paper, but John Beacon group. And basically, they talk about this new type of gamma ray source. So let me go to Cygnus. I was going to put some slides about the Cygnus movie, but there is a Cygnus movie, and do you know about the Cygnus movie? Check Película Cygnus, it's filmed at the LMT. There is a guy observing Cygnus, and with the LMT, he puts his earphones, and weird things happen. And there is a scene also at the HAWC observatory. But basically, here you have one of the things is the Cygnus OB2 region. In total, here you have like 1 million stars or 1 million solar masses on very big stars, in particular here. And basically, we studied this region. Cygnus is hard for HAWC because we have some sources. So these are the 3 Cygnus big sources. These are related to pulsars. So we have to remove these 2, make some fitting, have some clever students. I wonder if some tried the neural network, that sort of thing. But basically, at the end of the day, when removing these 2, we get a match spot on where is the Cygnus OB2 star formation region. And the spectrum goes well beyond 100 tera-electron volts. And basically, this is evidence that star-forming regions are also good cosmic ray particle accelerators, something that was not that clearly demonstrated. So that also made it to Nature Astronomy some time ago. me see. Okay, I'm doing time. Okay. Well, I'll keep going. And then basically one of our last objects is this near also bright source. There is this object SS433, which I believe it has a reputation in this institute. It has been observed by a few people here. It has those lines that precess, helium lines that precess and show that there is a jet moving at a quarter of the speed of light. So that made it, okay, that makes the name of a microquasar. So in black contours are X-rays, and basically there is a big X-ray emission at SS433, but there is also emission here, and this is right on the direction of lobes of the jets emitted by this microquasar. So when we remove this source, not we, somebody clever managed to remove this source, we get to these emissions that coincide with the jets, with the lobes from the jets emitted by SS433. And basically this is particle accelerator at the terminal shocks of this source. I'll put this one. This one was not on the top of the list, I'm sorry to say, but this was led by the group at INAOE. So Analia was part of the main authors of this paper. Basically, we made a study of AGNs. And until the arrival of HAWC, only 2 AGNs, and not by coincidence, the nearest BLAC objects had been detected at the gamma ray, TV gamma ray energies. That's Markarian 501 and Markarian 421. So we made a sample of like 130 objects that had been detected by Fermi at 10 giga electron volts. And we tried to see if we could find TeV, tera-electron volt emission. So this is our sample, the distribution. And you have 2 outliers, the 2 we knew, 421 and 501. And now this is the distribution of the rest of the sample. And then, as they say, the best of the rest were M87, these Veritas G521, and these are 2 BLAC objects and the radio galaxy M87. You may see this dotted line is a Gaussian fit. These are slightly above, not very convincing at the time of the paper, but then now with the past 5 survey, this group is now moving here. So we are starting to see AGN beyond the 2 Markarian objects, right? And finally, this is the sun. You can see this Paris-Texas comparison. This I took myself. We went to Texas to try to see the eclipse last year. And basically the sun, of course, cannot emit by itself gamma rays of these energies. No? Even the nuclear reactions are at the mega electron volt scale. There is no way you can get those. Solar flares are, they might get it to 1 giga electron volt, but that's about it. So this is basically the interaction of cosmic rays with the sun. So here you can see the Fermi emission, and here you can see what we detected taking 6 years of data from HAWC data. And basically one is the interaction of cosmic rays hitting the surface of the sun, producing gamma rays. And the other is cosmic ray electrons upscattering photons from the solar corona. So these are the 2 mechanisms in play. And what happens is if your sun is active, its magnetic field is shielding from the incoming cosmic rays. So there is an anti-correlation. The emission seen by Fermi and by HAWC is maximum in solar minimum and is minimum in solar maximum, which goes with this picture. Okay, so that's it about HAWC. So I'll go. So if I must finish now, it's okay, because now I'm with the competition. But basically now, when 2015, 10 years ago, we were the leaders in the field. We had the largest experiment in the world of this kind, the most sensitive, and for 4 or 5 years, we could basically study itself for ourselves. But then the Chinese, they reacted in 2015. They put some money, some yuan, Chinese yuans, 900 million of those, which is like, you know, like 100 million US dollars or more because the dollar was lower. So they basically put like 8-10 times more money than we did in HAWC, and they made something really big. 5,000 electromagnetic detectors and 1,000 muon detectors over a square kilometer. You know, and when we were 22,000 square meters, we expanded to 100 square meters. And they made a Cherenkov detector with 3,000 cells with 2 PMTs, so that's 6,000 channels instead of our 1,200. And then some Cherenkov telescopes just in case they needed more stuff. And there are 300 collaborators, China, Russia, France, Thailand, Pakistan. And this is what they made. That's LASSO. All these points are the electromagnetic buried detectors and muon detectors. Some are here, and they just basically buried. So these are all the detectors they buried around here. That's what they call the kilometer array, KMA. And here, this is the water Cherenkov detector. So these basically 2 medium size, basically HAWC size pools, and 1 double of HAWC. This is HAWC in comparison with LASSO. So they're taking up the field. This is a view. They're a bit higher than us, 4,300 meters, not much higher. So their main advantage is they cover a larger area, and they've been working now since, started in 2019, and by now they have a catalog. This is their sky map. You know, they also see the galactic plane. They go a bit further north. They are a bit further north. And their maps, they have displaced. This is the galactic center, which they don't reach. Now it happens that the southern sky now is a strategic advantage for us. And it's kind of hard. And also they are luckier than us. So we have not managed to detect the gamma ray burst. And 2-3 years on running, they got, basically the field of view of these instruments is such that you have 1 chance in 6 to have an object falling in your field of view. So it's like rolling the dice, and then they rolled the dice and it got spot on China, on Tibet. And they managed to have the brightest gamma ray burst that there have been for, you know, ages. So they had this amazing paper in Science. And the only good thing is that they have proven that if there is any other event like that that falls over Mexico, we will see it. If we are lucky. And finally, just to finish a couple of slides on where Mexico is involved. So the same way that LMT opened the door to have HAWC in Mexico, HAWC in Mexico is opening the door for Mexicans to collaborate in the Southern Wide Field Gamma Ray Observatory in Chile. The idea is to make an experiment that has more or less the capabilities of LASSO, but which will see the Southern Hemisphere, which is not explored at the same depth as the Northern Hemisphere. Since I made first this slide, now the site has been decided. It's in Chile, 4,800 meters, so it's a nice altitude. And this is still on the phase of getting money, meeting in collaboration meetings. This is in the Hotel Genève. Some of you, again, are here. And we're working on that. So now everybody wants to make field HAWC small. This is HAWC compared to the dense part of SWGO, 4 times larger, and to the sparse part. Still, this is like 10 times HAWC. It's twice the outrigger area, but it's like 1/4 of the kilometer array of the Chinese. So it's tricky. But the first SWGO tank is actually at HAWC. This one is smaller than, is slimmer, and you know, we're experimenting on that. So that's more or less where we are. We first more or less envisaged to have HAWC for 10 years, and suddenly 10 years have gone. You know, it's a bit Pink Floyd. 10 years have gone. But you know, 10 years after, we're not the largest experiment, but we're doing good and we still have ground to study things. Basically, we have already covered 11-year solar cycle, for example, that's for the solar studies, and we can also monitor the sky view. So that's HAWC and that's LASSO, and that will be SWGO, so we could also collaborate in more or less seeing that the performance of SWGO is similar to us. So we're trying to extend with a very stubborn SEMARNAT for 10 years our permits. And of course, this will depend on funding. So, you know, we could be running for 2 years, 3 years, 5 years, or maybe dismantle in a couple of years. It's still TBD. So, you know, it's still ongoing, and that's it. Thank you for listening.
Thank you. Let's thank Alberto. So we have time for questions. Danny? Oh, no. Yeah. Questions? Nobody? HAWC students?
Like
congratulations, you are here. You are very welcome to do some questions.
Will I get more data for my thesis?
Hola, buenas tardes y bueno, muchas gracias por la plática. En la página 50 mostraba una detección y decía al final que los modelos leptónicos eran favorables, pero sí. ¿Por qué?
¿Es en español o en inglés? In English, maybe. In English? Well, basically, when you get the spectrum, you fit. No? You make a fit either with hadronic models or leptonic models. In this case, the leptonic model goes better. I believe the hadronic model has problems to explain the radio part. Normally, that's where their weak spot. And also the slope also is more like consistent with leptonic models. And if you keep on attention, this paper, and for many of these sources, now we have the revised version. So we will be posting a new paper on SS 433 probably this year. We're working on that and basically extending the spectrum further.
Okay. Gracias.
It was not clear to me, what did you do to reach now the galactic center in your next catalog?
Yeah.
And another question, just is how many PhD theses has HAWC produced so far?
Yeah. So basically, we are, improving our algorithm. So from the past 3 to past 4, it was the better energy estimation with the ground parameter and the neural networks. The past 5, basically, we have got rid of more noise. Basically, because when you have one of these shower fronts, sometimes at low energies, they're more frequent, and sometimes there is a muon that's passing there, and you feed badly the plane because of the muon. So now we have a technique that is called the multiplane feeder that checks more than one plane and decides which one is the best one. And that allows to remove lots of signal. And we also have work on our pointing, which was deficient towards the south. So that has allowed to go from, say, 45 degrees to a bit more than 50. So we are seeing the galactic center, which has at 47. And one of our new Nature papers is of a source that is also at more or less 47 degrees from our field of view. So that noise rejection. In total, I had those numbers lately, but it's like 40 theses that we have produced here in Mexico between licenciatura, maestría, and doctorado. UNAM has made a lot, but also some of INAOE, and then institutions like Michoacana and BUAP and all have also made lots of theses, and a similar number of PhD theses from abroad. Yeah. Silvia, no?
Yeah, just a comment. I have the global number. I don't have the number now divided between Mexico and other countries, but as of December, last December, we had 70 between PhD thesis, master thesis, and bachelor thesis. And so that's the global numbers that students that HAWC has formed. Can I say something else? Sorry.
Yes.
Alberto was very kind to make my name when, in the AGN survey, but I just want to underline the credits. That was his work and of other two students, Sara Coutinho and Fernando Ureña, who did a great job in finding AGN. And the next survey that will be published, we have already 8 AGN detected with HAWC, so that's very important to say. 8. Well.
Yeah, and Sara Coutinho and Fernando Ureña, they're continuing their careers, one in Europe, the other in Costa Rica, so they're good success cases.
Alberto, if you're so lucky that you get funding for 10 more years and permits for 10 more years, what do you expect? What will we expect from HAWC?
Yeah, so we might be a bit less in the discovery space, but we can be on the also confirmation. So, for example, if LASSO sees something and reports something, they should report it at 5, 8, 10 signal to noise, 10 sigma. But that means that we should be able to see it like 3, 4. So we can do a follow-up, because otherwise you have an unconfirmed result that no one believes. So at least that part. Of course, we will work on the galactic center and southern sources, extending further on the south, on transients, and we have a good case for solar stuff that we have been seeing solar events for which decreases solar activity, you know, this modulation. So we can extend basically also our results that we have already produced to get better on that.
Can I will ask, Chucho? Okay, and then I have a small question.
What is the annual running cost?
Oh yeah, that's in fact, you know, we're not as expensive as, for example, our neighbor up in the mountain. So for the site to be operative is like 2-3 million pesos. And part of it we have we have the crew is paid by salaries from INAOE. So we need like a couple of million pesos. But then we produce 2 terabytes per day. So there's also similar chunk of money you need to keep the database running and growing. Just keep it running without growing is already a cost, but growing and running is also similar cost. Not sure about that number, but I believe it's also like a couple of million pesos for the data center here at UNAM, and also, well, the US has the same issue at Maryland. But you know, yeah, a couple of million. It's not that much for the site.
Yes, I want to know something about the collaboration in the South Hemisphere. Are the expectations, are how Mexican group is going to be involved? Their main objectives are the same?
Yeah.
Can you comment?
So SWGO is larger. It's like 14 countries. It has a big European involvement. So right now the 2 main partners are in a way Europe, Germany, Europe, and the US trying to get funding for the experiment. Of course, the good news is that we are in there, and I'll tell you a little bit. Partly with the prototypes, and we can use the site as but that's a minor contribution. But also, I was going to say about the funding. So the funding is not yet there. And one bad thing, for example, with the NSF is that HAWC and SWGO are like competing for the same pocket of money. Of course, we don't want much money of that. The SWGO needs more right now. So it's a good and bad thing. So in here in Mexico, we're trying to work together in both experiments, you know, and as HAWC can be something that helps SWGO development, right? Because from the science point of view, SWGO is now more attractive because you will explore the southern hemisphere. We know the galactic center is active and how far in energy. So our instruments are good to see the highest energies better than the Cherenkov telescopes. So how high in energy goes the galactic center? Centaurus I is very attractive. So there are a lot, a very good science case. So one thing that we are working is that in fact HAWC has 4 PMTs. So if we don't really get much more, one Mexican contribution, and we have more or less managed to see that it goes as a Mexican contribution, is that one of the PMTs of HAWC could go to the southern hemisphere and be part of a contribution. Now, again, that's a smaller contribution because, as you see, you need a lot of area and lots of PMTs, but that will be for the first phase of development of SWGO. 300 out of 12,000, 1,200, yeah. So that's one, and that would go at the end of 2026. Until then, 25 and 26 we're running as we are for the moment.
More questions?
We're hoping.
Okay, there's more. Question.
First, I understood that this southern observatory would be observing more galactic
Yes.
sources, right? And
Right.
HAWC was more centered on extragalactic sources. So, what do you expect on the extragalactic part on the southern hemisphere first? Mm-hmm. And the second question, I didn't quite get the explanation that you gave us about the solar observations with HAWC. Yep.
Yeah. So, well, it's kind of natural. Actually, if you've ever been to the southern hemisphere in a dark place and seen the sky, it's an experience. You should. So the galactic plane, that quadrant of the galactic plane is spectacular. It's very nice, and of course, it has been surveyed by HES, but not to the same energies and not to the same depth for extended sources. So that's a very good case for SWGO. Now there, aside from Centaurus A is brighter and nearer than M87, so, and also is, you can resolve it. So that could be an extended AGN, that's an interesting source. Where is the power, in the nuclei, or are electrons flowing to the lobes? And there is also a source, there is one very strongly varying at the declination minus 30 something, seen by HES, where variability is faster than what is expected by its size and all that. So there are some AGNs in the south. There is also O6. So there are a few AGNs on the south that have not been studied. And of course, the beauty of these experiments is that you scan the whole sky. So you can, as they say, you can go to the unknown unknowns. Things that you expect, you can see whether you see or you don't see, but then you find things that you don't expect, like we saw the TV halos. So are there, how many TV halos on the southern hemisphere? So there is a good case. There is a twin, it's further away, but there is a twin to the Crab pulsar, the southern, this J540 minus 69. So does that have a halo? Could we detect that halo?
Okay, let's thank again Dr. Alberto for his wonderful talk. Gracias y nos vemos el próximo miércoles.